Welcome, everybody. So today we are going to learn about two-slit interference. And the way this works is, as you can see on the screen, there is a distant source of light over on the left that sends some light towards the mask, which is a solid thing that doesn't let light through it, except for two very narrow slits, which have been cut in the mask so that light can travel through them. As you can see, those slits are separated by some distance, little d, and the light is going to pass through them and cause an interference pattern to show up on the screen, which I have indicated with little red dots over on the right. And our task is going to be to try to figure out where those dots are located on the screen. The way that we're going to do that is we are going to leverage what we know about interference already. So we found last week that constructive interference has path length differences that are integer multiples of the wavelength, giving us kind of 0, 2 pi, 4 pi phase differences. But for destructive interference, which is where you get dark spots on the screen, you're going to have half integer multiples of the wavelength for your path length difference. Once we know that, everything comes down to the geometry of finding the path length difference. And we know kind of conceptually that distance is the difference in length between the two lines that I have drawn here. So I'm imagining that I'm up there at the upper maximum bright spot on the screen. And I get out a ruler and I measure how far am I from one slit, and I get out a ruler and I measure how far am I from the second one, and then you take the difference between those two lines. To do that, I'm going to zoom way in on this picture and realize that as long as I put the screen relatively far away from the mask, those two lines are going to be parallel and the same length that you can see there, which means this little distance right here is going to be the extra distance that one of the light waves has traveled relative to the other. I can use some quick geometry to say that this angle theta is the same as the angle that you saw in the earlier picture, and that this is then going to be d times the sine of that angle. So this is now some pretty straightforward trigonometry that we are equipped to make use of here. And I can now say that if that's delta d, and I already know what delta d should be for constructive and destructive interference, I can set them equal to each other and be in great shape to solve for anything that I'm interested in solving for. The last important piece that we need to know here is we are often, but not always, going to make use of the small angle approximation when doing interference problems like this one. And one thing to remember is that the small angle approximation, which we've seen before, is only really valid for when theta is relatively small, less than 10 or 20 degrees. Sometimes you can push it up to 30, but then you're going to be off by a good like 10% or so. And in this case, the approximation that we're going to use is that if theta is small, then the sine of theta is approximately equal to the tangent of theta. And the reason that we make that approximation here is tangent of theta is way easier to use because we don't have to use any Pythagorean